Hi there, welcome to this lecture series on matrix algebra. Today we are going through lecture 7, part 1. The topic is computing the inverse of matrix. In this lecture, we will go through an algorithm to compute the inverse matrix, an algorithm that's much more efficient than the one we briefly introduced at the end of the last lecture. Okay, so let's get started. Okay, so let's set up the goal. We have a matrix A, it's n by n, a square matrix, and we want to find a matrix B, also a square matrix n by n, such that the B satisfies the following: A times B equals B times A equals identity. Then such a matrix B is called the inverse of A. So this procedure we're going to introduce here can be carried out under the following assumption. That is, assuming now we start with the A matrix, and remember we have elementary row operations we perform to do the Gaussian elimination. And then once that is achieved, we could do the backward substitution. And combine these two steps, we can transform the A matrix into the identity. And that's how we solve the system AX equal B. Okay. So we assume that this procedure can be carried out, that by a finite number of elementary row operations, we can reduce A or transform A into the identity matrix. Okay, so now we use the concept of the elementary matrices. So we know that every elementary row operation performed on the A can be achieved by multiplication by an elementary matrix on the left. So let's say the steps you had to take here would be can be represented by elementary matrix E1 and then E2 and then all the way to EK. And then this means I can multiply all these matrices on the left of A, and then this will give me the identity matrix. So basically this says that this group of matrices here, if you multiply them first, you will get a matrix out of this product. This one times A is identity. That simply means this matrix here is the inverse of A. Okay, so this is the basic idea behind the algorithm that we're going to introduce now. Okay, so here is an algorithm to find the inverse of n by n matrix A. So we will consider a composite matrix, which is m by 2n, as follows. We put the A matrix on the left and draw a vertical line and put the identity matrix next to it. The identity matrix will have the same size as A. Then this system is m by 2n. And then we perform a sequence of elementary operations on the rows of the A matrix so that the left portion of this matrix A will become identity. And as we are performing the elementary rows on the A, we do the same for the rows on the right, that originally identity block on the right. We perform the same operation as we do for the A. And we carry this out, and then we will have reached something like this. That is, where the A was earlier, it becomes the identity. And where the identity matrix was on the right here, it becomes some other matrix. Let's call it B. Okay, if this procedure can be done and reaching a form like that, then this matrix B here will be the inverse of A. Okay, let's give some justification for the algorithm. So, as we noticed earlier, performing elementary row operations on both the left and the right portion of this composite long matrix will be equivalent to multiplying each of them with the same elementary matrix. So let's say the first operation you took can be represented by elementary matrix E1. And then what you have will be E1A and then E1 identity. And then the second step is E2. And then you would have E2 times that. And then here will be E2 times E1 over identity. And then if you take k steps, and then you just have a sequence of identity matrix here on the left of A, and a sequence of the same sequence and on the identity matrix. And then if this procedure transforms the left portion into an identity matrix, then we have this one times A is identity. That means this product here in front of A, let's say this is a matrix B, eventually we'll call that. So this matrix times A is identity, therefore, and this matrix is A inverse. And then what will be this matrix looking like? Well, let's look at the part here. What do we have here? Will be exactly this matrix multiplied by identity, and which doesn't change it, right? So if we call this matrix B, what you have here will be B times identity, which is B, and which is A inverse. Okay, so let's take an example. We take an example of a simple 2 by 2 matrix A, which is here, and first row 0, 1, second row 2, -1. Okay, so we make this composite matrix, put A here, and put the identity matrix here. So the first step we see is that the pivot here is 0, which is not good. So we want to switch the row with the second row to get a non-zero. So let's switch row 1 with row 2, meaning we apply a elementary matrix E1, 2 here. Okay, so then I switch the whole row, including the one for the right half. Okay, so we got this one coming from here and this one coming from here. Now the next step is to make this turn 1. That is, we'll take the first row and multiply it by half. So perform E1 multiplied by half. Then I will get, all of these will be multiplied by half. So I get 1, -half, and 0, and half. Okay, now you see we are almost there. We just need to make this turn to be 0. Well, we can take the second row, multiply it by half, and add on top of that. That will make that term 0. Okay, so on row 1, add row 2, multiply by half. That's this elementary matrix. Okay, and then we would have half, add on top of here, you get a half. So we reached here, and we see that the left portion of this composite matrix now is the identity, and then the second half of it will be the matrix B, which is the inverse of A. Now, you might be a bit suspicious, and let's ease our mind by verifying. We can easily check that the B matrix is the inverse of A by checking if it satisfies the definition. Though that is, we can carry out the calculation of the product, A times B, right? So that's the A matrix and that's the B we found earlier, and we do this multiplication and then we see that. So, okay, so the first row, first column get me 1, and first row, second column get me 0, and you can easily verify it is the identity. And you can also check that B times A, which is the B is here and then the A is here. You carry out this product calculation, you easily reach also the identity matrix. Okay, so B is the inverse of A. So we have seen that not all square matrices can be inverted, finding the inverse. What if a matrix is not invertible? And where will we see this in the algorithm that it will break down? Well, let's take a look. We take the famous or the infamous matrix A, which is not invertible, and 2, 1, 4, 2. And let's try to carry out the algorithm. Okay, so we have put A and I together, which is 2, 1, 4, 2, and then the identity here. Okay, so let's try to make this 0. And we see that we can add on the second row, the row 1 multiplied by -2. Then this is 0. Okay, if I do that, then I get -4 cancels, -2 cancels, I get 0, 0. And here I will get a -2 on here. Okay, so we see that now we reach the state where this left half here is in reduced form, but the last row is all 0. When this happens, we see that there are no more operations you can perform to reduce this into an identity matrix. Therefore, we cannot find an inverse matrix of A, and A is not invertible. So we see in this example is that if the last row becomes all 0, or any of the row becomes all 0 in this calculation, then A is not invertible. Okay, so let's put the findings together and design an algorithm to find the inverse of A. Okay, so step 1, we write out this composite or augmented form M by 2n matrix. We put A next to an identity matrix. So we will perform row operations on the whole matrix, but the goal is to reduce the A into a reduced row form. And we know that there are finitely many steps we can perform to reach that. Now, once the A is in reduced form, let's take a look at it. If the last row of the reduced form of A becomes all zeros, then you stop and you say that the matrix A is not invertible because you cannot carry on. Otherwise, you carry on because now A is invertible. And then we will perform further elementary row operations until that the A matrix portion here becomes the identity, and you will have a matrix on the right half that will be the B. And then we isolate that B, which is the inverse of A. And then the algorithm is completed. Okay, so depending on the A matrix and the size of it, and this algorithm could take quite a few steps to perform and quite a bit to write out. Let's take some example to get ourselves familiar with it. Okay, let's be daring and put up a 3 by 3 matrix for A, which looks like this now. And then step 1 is to write out the augmented matrix. So put A here and put identity 3 by 3 next to it and draw a vertical line to separate them. Now we'll try to reduce A into the reduced row form. So look at the first column. We want to make these two 0, so this is already 0, so we just need to make this 0. What we can do will be add on top of row 3 the row 1 multiplied by -2, then this will be 0, right? So if you carry out that calculation, then you know this becomes 0, then this becomes -12 plus 9, which is -3, and that's -2, -4 is -6, and then here you get -2 on there, you get a -2. Okay, that's one elementary operation. Okay, so the next one is to look at row 2, column 2 here, and you want to make this term 0. And that, you see that you can take row 2, multiply by 3, and add on top, and you will get that. Okay, so let's do that. If I multiply 3, so 3, -3, I get 0. And then if I have 3, you get 6, -6, 0. And then 3, 3, I have a 3 here. So I reached here. Here I see that the A matrix now is in reduced row form. And then I check the last row. Whoops, unfortunately, it's all 0. So our algorithm tells us that A is now not invertible, and then we stop. Okay, let's take another example, hopefully more favorable. So here's the A matrix, and we write out the augmented form like that, and then we perform the following operation. We want to make this guy 0, so we would take row 1, multiply by -2, add on top of row 3, right? That's what we do. And if we do that, then this becomes -6. With 6, I have 0. -12, 12, I get 0. -2, 4, I get 2. And then I get -2 down here. Okay? So here we see that A is now in reduced row form. And check the last row here. It is not all 0. So we can continue. Okay, so the next step will be to make all the diagonal elements here to be 1. Okay, because that's the property of the identity matrix. It's all 1 over here. Okay, so let's take the first row. We need to multiply by 1/3. So that's this operation. And if we do that, multiply by 1/3, and we change the first row into this one. Okay, now let's look at the diagonal. 1, 1, 2, so this is not 1, so we need to fix it. We can take row 3 and multiply it by half. Okay, then we get 0, 0, 1. Multiply by half, I'll have -1 and half. Okay. Okay, so, but this is not done yet. And we'll still have to perform backward substitution to make these 3 0. Then this will be identity. Okay, and that we'll do on the next page. We'll start from this matrix. Okay, so we copied that matrix, the last one from previous page over here, and we're going to do operations on this one. Okay, so here there are different ways of doing it, whichever you prefer. Let's do the following. Let's say I'll try to make this 2 0. So what I can do is take the second row, multiply by -2, and add on top of the first row. That's this operation. Then this becomes 0, right? And you multiply by -2, you get -4. Plus 1/3, and you get that, and then this multiplied by -half, will you fill in here. Okay, and now let's make this element 0. We can take row 3 multiplied by negative 2 and add on top. Okay, and that's this step. Then that will be 0, and you multiply by negative 2 on top. You get 2, and multiply by negative 2 on top, you get negative 1. Okay, so we're almost there, and we see that the last term is this one. We need to make that one to be 0. So you can add on top of row 1, the row 3 multiplied by 11 over 3. Then this becomes 0. And you multiply this by the same factor and add on top of the first row, and you will get these numbers. Okay, so they look a bit complicated because this fraction 11 over 3. Okay, so now we see that we have reached the following form. That is, on the left here, it's an identity matrix, it's I. And therefore, this part here, it's a 3 by 3 matrix, let's call it B. And this one would be the inverse of A. Okay, so we have found an inverse for this 3 by 3 matrix. Okay, so that's all for the first part of this lecture, and later we'll talk more about the efficiency, how many operations it takes to carry out this algorithm, and etc. Okay, so I hope you enjoy this part. I'll see you later.